North America. I moved a little bit. Uh, I worked at McGill, University of Central Florida now for the last several years. Uh, so in terms of my research, what I do is described in this process. So what I start with is I build choice and econometric models with the objective of understanding human behavior and the overall behavioral process. So I classify my work as what is called explainable data analytics. So I rely on microeconomic theory-based approaches on why people are doing what they're doing and use that to understand travel decisions and travel outcomes. So I use a lot of econometrics, data analytics, optimization, and even microsimulation to develop large-scale regional transportation models for travel behavior and mobility. We also develop large-scale models for transportation safety as well in our group. We combine these advances to understand how households, firms, and communities interact in a system of system frameworks. So the frameworks that we have developed in our group have been applied in travel behavior by departments of transportations across the country in the US, but they're also applied by departments of public health to understand the transportation impacts on health in terms of air pollution, also in terms of how much walking people are doing, how is that helping their health, so different dimensions. So I work with public health professionals, I work with epidemiologists, providing transportation outputs to them from my group. In terms of my research, I work along 6 major themes. The first one obviously is infrastructure planning, which would be developing your high fidelity travel demand model so that we understand travel mode choices, vehicle ownership choices, how people use their time, and then how does that translate into travel. We do that so that we can actually provide patterns for mobility, infrastructure, and now transportation will play a major role in energy also, because as EV uptake increases, as more and more households and individuals start owning electric vehicles, our energy consumption was directly related to fuel in the past, but now even energy grid will be tied into transportation. The more you drive, the more energy you will draw from the fuel electricity grid. How do we plan for that? Because in the past, electricity demand was more predictable in the sense that you use a lot of electricity during the day, very little during the night. But now, if everybody is charging their cars in the evening, the energy demand profile might flip a little bit. So, how do we plan for that? So, how can we inform energy grid uh, proactively so that we can actually make changes to the energy grid so that it doesn't suffer from the any extra demand shocks? Roadway safety is an area that I work extensively. We have developed several models to better understand how crashes happen and how to reduce the consequence of crashes in terms of severity. How do we minimize? So crashes can happen, but when crash happens, how do we make sure that the driver or the passenger survive with as minimal injuries as possible? Again, this is a major issue even in India. I think this is something that will be important. Uh, we also work on emerging mobility, the emergence of different new modes such as bike share, ride share. Uber and Ola are now available everywhere. Also now the bike taxi is something in India that is very prevalent, and quick commerce, right? So we have everybody tells me things are much better in terms of quick commerce in India. You get anything you order in 10 minutes in India. Unfortunately, it's not that quick in the US, but that has its own impact on the transport system, as all of you are aware. So how do we model that comprehensively at a system level, and how do we incorporate and define what is its impact, positive and negative? How can, because it provides improved accessibility, elderly folks or folks who cannot travel or people are reducing their trips to accommodate to and purchase things without actually getting out of the house. There is positive benefits to it, but there can be negative consequences on these folks are under heavy deadlines. So how quickly are they traveling? Are they involved in traffic crashes because of that? What is the congestion introduced because of these riders taking goods from one place to another? All of these need to be studied in a systematic fashion. So this is an area that I work on. Public transportation. In the US, the public transport systems are not as heavily used as in India, but there are efforts to improve the public transportation system. So we look at ridership analysis. How can we improve the complementarity between public transportation and emerging mobility? So those are things that we work on. Again, I live in Florida as of now, and community resilience is a major issue because we have hurricanes, evacuation becomes an important part, flooding happens. How do we address these? And with changing climate, this is only likely to increase in different parts of the world. So I think this is something that will be an important area going forward. Also, I do not directly work in climate change area, but what I do is I work with climate change researchers and provide them expected emission patterns. So we have developed high resolution travel demand models that can provide emission estimates that feed into GHG estimation, greenhouse gas estimations, and then how climate will change 20 years into the future under different scenarios, 50 years into the future. So these are some areas I work on. I also work on sustainability. We are finishing we just finished a project for the Florida Department of Transportation, understanding how land use patterns evolve over time. And again, I think this is an area that is of importance in India also with the rapid urbanization and growth and so on. So in today's presentation, what I'll do is I'll focus on a econometric approach that we developed. As anybody who works with data knows, we don't get everything we want from one data set. So in this research, what we did was we were able to develop a method that can combine two data sets and build analytics that cannot be achieved with either of the data sets. Okay. So traditionally, all transport researchers use multiple data sets, but there is something common in the two data sets to merge data. So for example, we have uh, travel behavior data. People, we in the household survey, we have information on number of trips they made, what travel mode they used, how many kilometers they traveled, and so on. We augment that data with say land use or census data, where based on the person's location, we know what is the land use patterns around this person's house. So there is a clear one-to-one correspondence. What I mean by that is I know the person's residence location, census code, and then I match the census code in the census data file to add new variables such as how many people own cars there, what is the bus frequency in this region, what is the highway density around this house, and so on. So this is also a fusion, but I'm not talking about this kind of one-to-one fusion. So in that case, the fusion is well defined. We know what do we want to fuse because there is a common ID between the two files you can use to merge data. What I'm talking about in this algorithm is two data sets that are collected separately. There is nothing common among them. And still, how can we fuse them and how can we use that for model development? So the work is based on a paper I have here. So the idea that we are developing here is we are looking at how we can project EV demand. So electric vehicles are being purchased uh, at a very high frequency, but I would say the frequency has slightly slowed down in the last 2 years in the US. But still, the uptake has been very high. So with this, there is demand on the supply side. We want to ensure if people are buying electric vehicles, there has to be enough charging stations, fast charging stations, and so on. So understanding how EV uptake is happening, why are households buying or not buying, what is the choice happening is very useful. So we wanted to study that. And as you can see, this is the projected demand here for the EV uptake into the future. So in this research, we focused on two parts. One was we wanted to understand how people are buying a new vehicle, and then when they're buying a new vehicle, how are they choosing the fuel type? So the fuel type options can be hybrid, gasoline, or electric vehicles. So we are looking at these two options. So we want to understand why they're buying a new car, and then how they're buying, what type of car they're buying. So this is what we wanted to study. So we are using two data sets to conduct this analysis. The first data set is called the Merits CX data. This data has information on new vehicle purchases in the United States. All new vehicles sold are collected in this data set, but because they are this is a survey conducted by uh, the vehicle manufacturers and so on. they are not looking at it from a transportation perspective. They are not looking at, okay, you're buying a car, how many people are in your household? What is your income? How much is your, what other cars do you have? Again, they don't ask those questions. They simply ask, what is the model you're buying? What is the price you paid? What are the features in the car? So it's kind of a survey made at the dealership kind of a thing where when you're purchasing, you get this information. But that, while it is very useful, is not helpful to do transportation planning models. So what we wanted to do in this study was to look at how can we combine this rich vehicle purchase data with a nationally representative to household travel survey. Okay, so we selected a household survey data that is available for 2017. We look at information in that. So this is a nationally representative survey data. So we ask all the questions that we ask in a travel demand survey. We ask them what are the travel patterns, how many vehicles are there in the household, how many trips they make with each household, how many people are in the household, what are the employment status. So this is a very rich data set that can be used to model travel behavior. But unfortunately, it does not have any information on the kind of cars people are buying. So these two data sets provide rich information in their own way, but they'll become even more powerful if we are able to combine them to do our analysis. So merits data is it has a limited sample size because it only focuses on the group of people who are making vehicle purchase. It doesn't look at the universal population. We have no information on how they decide to buy the vehicle. We only know people who are buying vehicles are represented in that data set. So what we want to do now is we want to merge this data set that is applicable only for a sample of vehicle buyers with the full population, so we can get important variables from NHTS and understand clearly what is influencing vehicle purchase and what is influencing vehicle type choice. Of course, it's a nice thing. We want to merge both of them, but there's nothing common. They are two data sets collected by different survey groups, different respondents. There's no reason to believe that the same person will appear in both of them. So that is the challenge. So what we are going to do here is we are going to suggest that yes, we recognize that these are two different data sets, and the people in data set 1 and data set 2 are not common. But there are some common attributes that exist in both datasets. So the common datasets attributes can include the location where people live. So there is a survey respondent in Merits who lives in an urban area. We have a survey respondent in NHTS who also lives in an urban area. Then the age category of the person buying the vehicle could be a common attribute. Similarly, income category, the state in which this vehicle is being purchased could also be a common category. So we use the different common attributes that exist in our two data points. So we are not, the first point we need to recognize is we are not saying that the same person is there or same household is there in both surveys. We are not saying that. What we are saying is, okay, that's fine that nothing is common, but there are some common attributes between the two cases. Can we exploit that? Can we use this commonality to create a data set that will allow us to predict things better, to understand travel behavior better? So if we are able to do that, we will get all of these additional variables. So gender, race, home ownership, household size, vehicle availability, number of workers, all of these variables are very important in doing any prediction of vehicle choice behavior. So suddenly Merit's data set will be richer because we get all of these additional variables. So that's what we want to show. So let me illustrate this with a data set here. So this is on the left, we have the Merits data set. On the right, we have the NHTS data set. So this is how the information is available. So if you look at households here, we have household 1, 2, 3, 4, and we see age, state, vehicle type, and fuel type. If you go to NHTS data, you have household ID. So here we have only, in the Merits data, we only have one record per household. In NHTS data set, we have multiple records per household because there are person level data. So here we have, in household 1, we have some information. We have household size, we have household status. So here I am looking at age and state as common information. So if you look at the two data sets, I compare. So for household 2, I find two matching records in NHTS data. So there is a person with 37 years age living in Florida. There's another person, 37 years old, living in Florida. This person lives in a two household family. This person lives in a one household family. Both of them are renting. So what I do is once I find a match, I keep adding that. So you will see that for person two, there are two matching records here. And once I match them, I add these two columns of data from the NHTS dataset on the next. So basically, I'm building a fusion dataset by saying, okay, I will focus on age and state. If there is commonality in age and state, I will bring the information match. Now, as you can imagine, with these two variables, there could be many matches. So there could be 20 matches, 40 matches. And it's valid to consider all of them. So we need to evaluate these matches carefully. Also, the other question is, why should only we consider age and state? Why should we only consider age and state? We can consider other variables also. Again, very valid. So we have to create a systematic process to understand the matching and using that. We'll do that. But before we do that, I want to show another step we need to do. So if we are matching it this way, what is happening is we are replicating this record. So here that record is available only once, but because we matched it two times, we have the fused data set, it comes in two cases. So that a record with more matches becomes more important because you have more matches. But we need to recognize that all of these matched records should represent only one person in the original data set. So there are several ways of doing it. One way of doing it is what is called the equal weighting approach. So what we'll do is, okay, we found two matches. So each of them contributes half to the original data set. So we add a new column, call it weight, and say each record has a weight of half. Okay, that is the naive approach or the very simplistic approach. In this research, what we did is we said, can we go one step further? Can we recognize that all of these add up to one, but some records might have a higher weight versus other records? The reason I'm saying that is we match records based on two variables. There could be other common records that I'm trying not to match. Okay, so now if those match, the weight can go up. If they don't match, the weight can go down. So the reason we considered this approach is because when we tried matching with all variables, sometimes for some households, the number of records that match were very small. Maybe there is only one record or there is not even one record that matches. So what we decided was, okay, let's not try to match with everything. Try to match with a subset of records and then use the non-matched records as a way to differentiate. So for example, age and location, age and state match, and then location type matches for some records, it doesn't match for others. So a household, if the original survey record was from urban area, and if the record that we have, in addition to age and state, matches with the urban area, we provide that a higher weight compared to a record from a rural area. So this again, I don't decide what is the weight. We let the model decide. We maximize the log likelihood function that we create for this complex system and figure out which matching variable is important, which matching variable is not important. So that way, our focus is on understanding vehicle type. How well can we predict our vehicle type by using different matching variables and different unmatched variables? Okay, so this is the big picture process of how we are fusing the two data sets. And because there are a lot of variables, so somebody might say, why only location should be the match, or maybe sometimes location is a match, other three are unmatched, might be better than location, age being the match, income, state being the unmatched. So there are several possibilities. So we designed an experimental process to test all possibilities. So we only match with location and try everything as unmatched. We only match with age, try everything else. We match location, age, location. And as you can see, there are several possibilities that you can do. And then you can also worry about, okay, how many records should I match? Sometimes if you're only matching on location, we get 100 or 1,000 matches. I cannot keep running models with thousands of them. So I randomly sample 10, 20, 30. So even that number we tested and to see what is happening. Okay. So let me talk about that. So because there is a lot of randomness involved in how matching happens and how what records we choose, we need to make sure the randomness does not make results significant. So we ensure that we test different samples. So we start with 5 records and do 10 samples of that and see how the model results change. Okay, so we have common identifiers. We have the weighting process that I talked about. So we match by location and age. We combine 5 records and estimate the models. Again, I'll show the results as we go forward, but I want to explain the fusion process. So once we do this, we change the set. So we looked at age and location. Now we try other values. So we repeat this process to make sure we are getting reasonable results. And then we identify the optimal numbers of, okay, what is the optimal independent variables for matching, independent variables for not matching. We identify the sample size. All of these are rigorously tested in this process. And then we check for parameter stability. If the parameters are stable, we go over and get our final model results. If the parameters are not stable, we make sure we drop that variable and go back and run this process. Again, I won't go into too much of the mathematical details. The model systems are simple. We are using a multi-logic model here, but that is fused. So we have the main new element is the weight element. The weight component determines what should be the weight for each fused record, so that if you are fusing 10 records, the 10 records add up to 1 record in the original dataset. So we are not artificially adding data. We are just using NHDS dataset to inform. So we have 10 candidates informing us about 1 merits record if we're matching 10 records. But the net contribution of that 1 record adds up to only 1 record. This is the log likelihood function that comes up after using the weight function. Okay. So we tested a lot of combinations here. I'm showing the top 6 or 7 combinations here. So you'll see age and location, age and income. So this, what I'm showing here is the improvement in prediction, improvement in how well we can understand vehicle type choice, right? So our objective is how well can we predict whether the household picks a gasoline vehicle or a petrol vehicle versus an electric vehicle. So these are model improvements that are being shown in that model. So if you don't do any fusion, I can run this model using a single dataset. I run this model with merits dataset. The best model I can get, that becomes our benchmark. After fusing, if your model does not improve, it's all a waste. Don't do the fusion, right? If your fusion effort is not showing improvement in how well people buy which type of car, we don't want that. So what we are testing here is the benchmark is the best model with the single dataset. Compared to the benchmark, how well are these fusion models doing? So you'll see that the income and location model offered an improvement, significant improvement in understanding the choice. For that combination, we ran different number of fusion records. So we fused 1, 5, 10. You'll see that as we increase the number of fusion records, it improves in the beginning. After a point, it stabilizes again, which is a good thing. So if you have more fusion records, the runtime increases, even because we have to, if you have 1,000 merits records and if you're taking 15 fusion records, your dataset becomes 15,000. So we want to find an optimal value that is reasonable. So we based on this, we selected 15 as our number of records, because after 15, the improvement was not significant. Another thing we did is when we select 15 records, these are randomly selected 15 matches. So we wanted to make sure if I randomly select another group, the results do not change. So we run what is called a model stability test that we created. So basically what this recognizes is, if I run 10 samples, are the parameters changing wildly across these samples? And if the parameter goes beyond 1.96 is when the parameter changes wildly. But you will see that this modified t-test, everything is less than 1.96. So what that tells me is across the 10 samples that we are testing, the parameters do not change that much. Again, which is a very good result. It's telling us that even though I'm taking randomly 10 samples, all 10 samples exhibit the similar behavior. So you'll see there are 1 or 2 outliers. For example, here there's 1 outlier which goes close to 1.9, but still the numbers, the averages are very are very small and much lower than even one for most cases, for most variables. So only these two variables, we get slightly higher values for one or two records. And as you can see, the box plot, the majority of the records are still under 1.25, even for the worst variable. So the variables that we considered for the vehicle choice model are the fuel type and vehicle type. For the vehicle purchase model, I'm looking at a binary choice where we are focusing on whether this household will buy a new car or not. Okay, so again, with that, I will show you that because we had multiple fuel types like hybrid, electric, and so on. We did not have enough sample shares for those, so we focused on gasoline versus non-gasoline. So these are the individuals or households who will purchase electric vehicles. We also looked at the vehicle type. We wanted to understand what type of vehicle they're using, gasoline and non-gasoline. So we have pickup truck, sedan. So we have 8 alternatives. We have 2 types of fuel, 4 types of vehicle types. So we created 8 alternatives. So gasoline, utility vehicle, gasoline, sports sedan, gasoline pickup. Similarly, everything for non-gasoline. So there are 8 alternatives in our vehicle types. The independent variables considered in our model, they come from different categories. There are vehicle characteristics that we considered. There are spatial factors that we are considering. We are considering household economic characteristics and household demographics. So all of these, again, traditionally what we'll use in any vehicle choice model are considered in this model. In terms of the results, so I'm showing you the results for the vehicle choice model. Here we are looking at the 2 dimensions. There is the gasoline versus non-gasoline, and there is different types of vehicles. So because there are 8 alternatives, you can estimate 7 coefficients if we do a traditional multinomial logit model system specification. But here we do it by the majority dimension. So we look at gasoline versus non-gasoline, and we look at the vehicle type, and then we'll do interactions if we need for combinations. So you look at different independent variables here. Vehicle fuel efficiency, if it is an important factor, then people buy non-gasoline, it becomes preferred. If vehicle price, if you're considering as vehicle price increases, people don't buy people reduce the chance of buying, it reduces the chance of buying a sedan. But the higher the price, people who are interested in sports sedans buy those at a higher price. Same thing with pickup trucks, because again, these types of vehicles come with several features in terms of high acceleration, high features in the pickup trucks and so on. So people are willing to pay extra. So, but only people who are buying sedans are price sensitive. Again, this is general. So this is something a middle income person would be looking at. Sports sedans and pickup trucks are purchased by people who have higher disposable income at some level. So these folks will be purchasing that with higher cost. Similarly, engine size, again, as it increases, people have less chance of buying sedans. We also have some brand variables here, the different brands available in the US. So Toyota, Subaru, Ford, and so on. So these serve as fixed effects. They're just controlling for factors related to brand that we cannot control in other variables. Then we also looked at environmental economic characteristics such as household income. High income folks don't buy pickup trucks. We have age. Again, as age is higher than 65, they tend to prefer sedans versus sports sedans. Now, until now, these are all variables that we got from Merit's data. The next part is where the variables from NHTS were included. So renting a house or not, if you rent a house, there is higher chance that you buy sports sedans, lower chance that you'll buy pickup trucks. We also looked at some demographic characteristics. Population density is considered. If you have low population density, you're likely to buy non-gasoline and less likely to buy sedans. Again, proportion of male versus female in the data set also has impacts on different parts. So the higher the proportion of male, as you would expect, the higher is the proportion of pickup trucks being purchased. And in terms of the weight specification, we found that because our matching was based on income and location, we were able to differentiate behavior based on age. So age was not matched. So if the difference between the age was small, the weight was higher for that matching record. So if I have 3 records which have the same location and same income. Records that had closer age match offered a higher weight. Again, it makes sense because that tells us that these people are in the same life cycle. So, for example, I live in the same location and have the same income as another person. But if I'm a 40-year-old and the other person is a 65-year-old, our behavior will be different. So, the contribution to the original record should be higher when the age matching is higher versus when the age matching is lower. That's what is being reflected in this result. So again, this is one example application that we developed this fusion for. There are several possibilities where we can use this fusion approach. So here uh, we conducted other studies where we wanted to study energy demand. So again, there also there are energy surveys that are conducted by US Energy Administration. But again, they focus purely on energy consumption in a household. What they did not recognize at that point was there is no EV charging at home. So their surveys are not designed to tie energy demand to transportation usage. So RECS is the energy survey. So we combined that with a national household travel survey to show how knowing more information about travel patterns can affect energy demand. So we conducted a couple of papers on that area where we use this fusion. So the first paper is where we actually proposed this method for the first time. The second paper is where we applied this method for energy sector in a multiple discrete continuous context. So here in the fusion exercise here we did is using a multinomial logic model where you are choosing one out of the 8 alternatives. But there are choices where you choose multiple alternatives out of the many alternatives you have. So for example, if you think about households with multiple cars, there are people who have 2 cars. So they're buying one sedan and one SUV or one small car and one big car. So there they are choosing multiple things. So same thing can happen if you think about your retirement portfolios. People who are into equity and debt. So you put some money in equity, some money in debt. Again, you don't choose only one. Again, there are people who do that. There are people who will never do anything except fixed deposits. There are people who will buy only shares and not do debt. But what we are saying is majority of the people will have a mix of multiple options. So an MNL model cannot handle that. You can use more sophisticated models such as a multiple discrete continuous extreme value model or other frameworks like that to do that. So we illustrated the fusion approach with that in this case. Then we also used it to conduct analysis of a hurricane evacuation behavior. So in Florida, this is a big issue. We have a lot of scenarios where hurricanes go across major urban regions. And because Florida is like a peninsula, there are only 2 highways running through the length of the state. So everybody evacuates using those 2 highways. So because of that, traffic congestion becomes a major issue. There are crashes that happen. And the bigger challenge of people are not able to go away from the hurricane, right? You don't want people to be stuck on the roads when the hurricane hits. So this is a major area of research that happens in Florida and other parts of the country. What we did here is we were able to get access to a social media data set from Facebook, which provided us geolocations of people evacuating from different parts of the state. So we were able to identify their location before the hurricane and after the hurricane. So these are self-reported data. It's a very rich data set. But the problem is, as everybody knows, as the age of the person increases, the way they use social media reduces substantially. So these data are not representative of the population. Yes, I have a million records in social media telling me what people did. Now, can I use that and apply it to the population? No, because the first limitation of social media data is it is very skewed towards a specific kind of person. Not everybody who evacuates reports, self-reports on Facebook. Everybody is not posting their updates on Facebook. So what we wanted to do was, okay, how do we use a known biased data set and combine it with a well-representative population sample? Again, here also we use NHTS dataset because NHTS dataset represent households that are statistically weighed in the population, and represent the weight represents how many people like that exist in the dataset. So we were able to combine the Facebook data using and the NHS data using the same process with the objective of predicting their evacuation decision. So we fused the NHS data with the Facebook data to understand who is evacuating and what are the reasons why they're evacuating and what can help us predict that better. Now, once we do the fusion, because we have population weights in our sample, we could use population level predictions from that fused dataset. So we were able to actually match. So we had a major hurricane called Hurricane Irma in the Florida region. So the number of people who evacuated at that time, again, it is measured. Nobody knows exactly. So we know that the range of that evacuations were between 2.5 to 3 million or something of that order. So using our approach, we were able to do two things. One is better understand the factors affecting the evacuation decision, but also come up with a population estimate that was very close to what was reported. So we were able to get to between the range of 2.5 to 3 million, we were able to estimate using Facebook fused with NHTS. Right? If you use only Facebook data as if it was unbiased, we were predicting 2 times the number of people that really evacuated. Because again, the Facebook data is a self-selected sample of people who are evacuating. So if you take that as the representative population, you will overestimate the number of people who actually evacuated. So by combining it with the NHTS, we were able to actually get to a more realistic range while creating a more representative population of the sample. So again, these are the different approaches that we can use. The same approach can also be very helpful, especially in a country like India, where data is harder to get. I think this approach will have even more power because we get different disparate data sources. There is some information here, there is some information here, but if we can fuse them using these important variables that are common versus different across the two regions, we will be able to get to a better fused data set that is more representative of the population behavior. Okay, so again, with that, I know we have 15 more minutes now, so I'll like to open up for questions. So again, thank you for patiently listening to my talk. I'll be happy to answer any questions here.
Thank you, sir, for this insightful session. We truly appreciate the time and effort you took at such an early hour to deliver this session for us. Thank you so much, sir. Now, the forum is open for discussion. You can also ask questions through the chat box.
Thank you, sir. This is Anish from NATPAC. So it was a good presentation, sir. I like the whole idea that you're using. I would just like to know if there are no matching records, then how do you propose to do that fusion?
Yes,
because NHTS is also a sample-based one, so we might have some which are not matching. So in that case, what would be done?
Yes. So for example, let's say we are looking at age only for to a good question, very good question. I'll explain. So let's say we're thinking age is the matching point, and what you are suggesting is there is a 22-year-old in the merits data set or the first data set, but there is no 22 household person in the other data set. Okay. So that could be a problem if that happens on a large percentage. Okay. So in our case, when we chose only one variable, we were able to find matches. Now, if it happens that lot of records are not being matched, what we can do is, it is not required that we need a match. So we can start the fusion process with no matches. So randomly, I will randomly fuse 10 records with my source dataset. So I'll call the first one the source and the second one the feeder. So I take one record from the source. I just blindly fuse 10 records. Right? The idea is, can these 10 randomly fused records add any value? Now, somebody might say, yeah, how will they add value? They're just randomly chosen. Yes, you're right. So age does not match, but I can find the differential. So age is 22 in my source record. My feeder record, one age is 32, one age is 42, one age is 52, one age is 62. So I will use the age differential as the weight without any matching and just apply the same process. So the the approach is general that way. So we don't, if it is there are matches, we have noticed that matching some records improves the model fit. Okay, but if there is no matching, no problem. You can still take the records randomly and then look at differential. So for example, there is no matching, but you can say household income difference, age difference, incorporate those into your weights, and that will give you a different varying weight across the random records, and hopefully it will contribute. Again, the decision to whether to do fusion or not is not decided by me. It is decided based on what is the value to the dependent variable prediction, right? So if I run my model without any fusion and I get a model, after I run my model, after fusing, this model should improve my model, right? Compared to the benchmark. If it doesn't improve, your fusion is not working. So we have a very nice way of testing it. Only then we apply, right? So you can match, to answer your question, even if there are no matches, this method is applicable. But obviously, it might become less useful, right? Again, it's like randomly throwing two things at each other and saying we're trying to match. So there should be some commonality, right? As long as at least if 40 to 50% of the records have matches, it will help a little bit more. Let me put it that way. Because if there is nothing matching, why are we fusing the two data sets, right? I mean, if I have a data set of one choice and other choice, there should be something similar in the two data sets for us to consider fusion. Even if these attributes are not exactly matching, we can still use it as long as the two data sets are relevant to the choice process. Anish, I hope that answers your question.
Yes, sir. Yes, sir. And also, I would like to ask how we are validating it. Is any data being collected in the field to validate what we are proposing?
So what we do is we actually keep some records from the original sample on the side. So if we have let's say 10,000 records, I only use 7,000 for model development, and we keep aside some records that have never gone through the model, and we use our model to predict the behavior there. So we're able to see. But your suggestion is very well taken. It will be nice if we can get to do the field collection and further validation. That also is a good step. We'll probably look at it in future efforts.
Okay, sir. Thank you. Thank you.
Yeah, as we just give me, sorry, one second. As we, again, I have a bit of a news. I'm actually moving to India, relocating to India as a faculty. Again, I'll be joining IIT Hyderabad. So I just wanted to let all of you know. I hope I can interact with you more often once I'm there. Yeah.
Oh, that's great.
Congrats.
And congratulations.
Thank you. Yeah. Sorry,
Sir.
go ahead. I stopped somebody from asking questions. Sorry.
Yeah, Ilangon sir.
Yes, I was in your initial slide. You mentioned about your work on road safety field.
Yes.
So, how modeling crashes to enhance our understanding of crash occurrence and severity? Have you done any work on it? Could you please elaborate any work that you have done in the past?
Yes, I would say close to half of my work is on that. So I again, you might be aware of the highway safety manual in the United States.
Yeah.
Yeah, so I do a lot of NCHRP projects, so National Highway Cooperative Research Program, that feed into the highway safety manual. So I do work on, right now I have three. We finished three NCHRP projects. I'm working on three more that are going to be wrapping up very soon, where we look at the impact of vehicle. For example, one project we finished is looking at the impact of vehicle mix on crash occurrence and crash severity. We did this for all facility types across United States. I'll be happy to share the final report. That is, again, it's an NCHRP report. We're currently looking at effect of speed on crash frequency and crash severity on rural highways across the country in the United States. We looked at weather impacts on crashes in another project. I also do a lot of academic work looking at more sophisticated methods on capturing crash frequency and crash analysis, especially at the macro level. So we call that safety planning at a macro level, trying to understand what factors are increasing crashes, what factors are increasing severe crashes. So I do segment level analysis, zonal level analysis also. We have done work on that. So again, all of my main focus is, again, everybody knows you don't wear a seatbelt, the severity increases. You are going, crash happens, there are more high speed roads, more severity happens. Again, my objective is to do the quantification accurately. What is the impact of not wearing a seatbelt versus drowsy driving? What is the quantitative impact? How do we get to the number that, so which is more important as a policymaker to address? So we've worked on that. So if you want more details, I'll be happy to email you all the reports that I mentioned here. They're also available on my website. So does that give an idea? Again, I don't know.
Yeah, I think, do you use the crash data that are recorded by the police and other agencies? You are using the behavioral aspects of the driver?
No. So there I'm doing crash data. So I look at crash data collected by police, collected by hospitals. We have used different kinds of data sets for analysis. But we look at, so in one project for FHWA, we looked at behavior also by focusing on trips. So we said, again, nobody the outcome of a crash is dependent on the actual trip, right? So somebody started at their home, they were trying to go somewhere, and they were involved in a crash, right? So to truly understand how crashes happen, the current approaches to safety, we look at a snapshot. Okay, this person got injured in this location. We'll try to understand what happened. But understanding where the trip started, where the trip was destined, and what kind of car they were driving, how long have they been driving, if you are able to generate that kind of data, it'll actually allow us to better predict the chance that a crash happens and what is the impact of that, right? Because a person driving 1 mile from their home versus driving 200 miles or 200 kilometers from their home, the risk profile changes a lot. We don't consider that when we model crashes right now. So for an FHWA project, we did analyze behavior also as part of it. But again, that is not standard practice yet. It's not the state of the art in practice. So we switch between, depending on the sponsor, we have to switch between what we can do for them. So we look at behavior when possible. We analyzed the naturalistic driving data from Virginia Tech. We use that to study that problem because that requires a lot more data than just crash data, right?
Yeah, I think the International Road Assessment Program looks at the road factors and the vehicle factors and such things for modeling the crash occurrence and severity. So, do you use such data? Or do you use one purely the behavioral aspects of driver?
No. We use all data. So I look at roadway geometry, speed limit, the width of the shoulder, width of the median, everything. Again, everything available, right? Sometimes curves are available. If the curve radius is available, all information, as detailed information on roadway geometry, traffic volumes, everything we use, because behavior, yes, is important, but that's not the only component that affects the crashes, right? Because if you want to suggest policy makers what to do, what remedial measures can we do in the roadway geometry to reduce? Okay, given a crash happens, how do we minimize it? So we look at comprehensive factors. We look at environmental factors like whether it rained, what is the visibility. So all domains of variables you can think of, age of the driver if possible, vehicle age, all variables are considered.
Okay, thank you.
Any more questions?
Thank you, sir. Now, I would like to invite Ms. Adra S. Krishna, Junior Scientist, Traffic Engineering and Safety Division, to deliver the vote of thanks.
Thank you, Soja. Good afternoon to everyone, and a very good morning to Dr. Naveen Eluru joining us from Florida. It is my privilege to propose a vote of thanks for today's technical talk on the topic Emerging Econometric Modeling Approaches for Travel Behavior Modeling, conducted as part of our 34th Transtech Technical Talk series. On behalf of NATPAC, I extend our heartfelt gratitude to Dr. Naveen Eluru, Professor, Department of Civil, Environmental and Construction Engineering, University of Central Florida, for delivering such an insightful and enriching session. The talk highlighted a novel econometric framework developed by their research team to fuse data from two disparate sources. Dr. Naveen Eluru provided an overview of the approach, explained the approach through his research on building fused data sets to model travel behavior, integrating the vehicle purchase data as well as the National Household Travel Survey data to understand the factors influencing new vehicle purchases, consumer choices, etc. Dr. Naveen further discussed its potential applications across various transportation domains. We sincerely appreciate the time, effort, and depth of expertise that went into preparing this outstanding presentation. Now, I would like to thank our director, Professor Dr. Ashalata R., the division heads, the organizing team for their dedicated efforts behind the scenes in planning and conducting this session so smoothly. I would also like to express my sincere gratitude to all the participants for their active engagement and valuable appreciation throughout the program. I would also like to extend a special mention and heartfelt gratitude to our former director, Sri T. Elangovan sir, for honoring us with his esteemed presence today. We are truly privileged to have benefited from his valuable insights and contributions. Once again, thank you all for making this event a meaningful and successful one. We look forward to many more such enlightening sessions in the future. Thank you all and have a wonderful evening.
Thank you, sir. Thank you, sir. Thank you, sir.
Thank you so much for the invitation, and I am happy to have presented.
Okay, welcome, sir. Welcome back.
Yeah, thank you so much.